It's my pleasure to introduce our first speaker. Today's speaker is one of our star faculty member here, Professor Arka Majumdar. So on this campus, Arka does not need introduction, but I just enjoying reading his achievement and his career path very briefly with you. Arka got his PhD from Stanford University in 2012. Then he spent 1 year doing postdoc at UC Berkeley, then another year at Intel before he joined UWECE as an assistant professor in ECE and physics. So his research covers a broad range of nanophotonics. He will tell you some of them today. But his distinction and awards, a long list, I'll just read a selected pieces of that, including Young Investigator Awards from ALFOS, Office of Science and Research, National Science Foundation, ONR, and DARPA. He's also many others as well. But I'd like to mention he's a co-founder and a technical advisor currently of a startup company, 2Optics, which is actually becoming more and more successful, I heard. A lot of exciting news. All right, so without further ado, I'd just like to welcome Arka to give this very first talk. Thank you very much.
Hey, thanks, Mo, and thank you, everyone for coming. So as Mo mentioned, my name is Arka Majumdar. Most of you probably know me. So I'm going to talk about some of the work that we are doing probably over the last 5-6 years, which we called is creating a programmable gate array in optics. So many of you probably know electronic FPGA or field programmable gate array. And the idea is you have a generic circuit, and you can program that circuit to make it for any different applications. Right? It turns out, even though that is something very, very well known in electronic community, we don't really have that functionality in optics. And one of the research goals for us was that can we actually create some of those kind of optical programmable gate array? And it turns out it's not field programmable, it's current programmable, but it's still programmable is what I'm going to talk about today. Most of the work that I'm going to present, if you want to see the papers, you can find it from my group website. And if you have any questions, you can always email me. OK, before I start, I'd like to acknowledge my team and funding, especially Zuran and Rui. Both of them are ECE students who did a bulk of the work. And Jiaju, who was my also ECE student who graduated and now works in analog photonics. And this work is primarily supported by several Department of Defense grants, but also specifically I would like to point out Intel, because we are actually working with Intel in a center to put this kind of this new material that we are going to introduce called phase change material in Intel's silicon photonics. Before going, let me just very briefly tell you what else is going on in my lab. So the work that I'm going to present is not all the things. So my lab's main interest has been to understand the interaction between light and materials. And it turns out when you take light and you confine them in a very small volume, and when you say small volume, we mean sub-wavelength volume, for a large amount of time, you can start increasing the interaction between light and material system. And that gives rise to some interesting effect, is what we really want to study. And to do that, we design and fabricate various nanophotonic structures. We call it nanophotonics because we take an optical, let's say, surface, and we pattern them in the sub-wavelength scale. Now, knowing that the visible wavelength is between 400 and 700 nanometer, and most of the optical communication that we are interested are in 1300 and 1500 nanometer range, when you pattern in sub-wavelength, this feature size becomes 100 to 150 to 200 nanometers. So that's why we call it nanophotonics. So we design and fabricate these structures. All the fabrication we do here in the university using Washington nanofabrication facilities. We have a pretty good shared clean room here. And these are generally made with silicon, silicon nitride, or gallium phosphide. Although in today's talk, I'm primarily going to focus on silicon. Now, once we make this structure, we actually put a lot of different kind of materials, and we have collaboration throughout different departments in the university and outside the university. One of the material that we have a big program on this kind of atomically thin 2D material. So graphene is one of the example, but many other 2D material, we are doing a lot of work on that. We are also working on various solution process quantum materials in collaboration with chemistry, using quantum dot, colloidal quantum well. And then this another material that will be today's main focus is phase change material. I'm going to discuss what that is. This material essentially undergoes a phase transition, which is a non-volatile phase transition, and we are interested in seeing what can we do with it with this material integrated with silicon photonics. And with this basic platform, in my group, we are pursuing kind of 4 different research directions. In one of them, we are very interested in understanding, can we do quantum many-body simulation using strongly correlated photons? If we can engineer interaction between photons, can we use that to make something, to simulate a complicated quantum system? That's one of the research directions. Another one is this nanophotonic computational image sensor. So here the goal is that can we make very small image sensors using some of this nanophotonic technology. If you look into current cameras or any other imaging systems, these are primarily done by refractives, which are bulky and also have large weight. Can we actually replace them using some sort of nano pattern surfaces? And with that is the thing that we call meta-optics. So 5 years back, actually, I gave a department colloquium really talking about this. And it turns out that when you make this kind of small optics, there are some fundamental limitations that come from diffraction. And you cannot really overcome that just by engineering. So we look into some computational backend to co-optimize that optics and computational backend together to make very small image sensor. And one of the main focus right now in the group is making very, very small endoscope and angioscope for cardiovascular disease, both diagnostics and therapeutics. Using the same platform, we are also looking into creating kind of an optical neural network accelerator. So can we use just the wave propagation of light, exploit that to solve a machine learning problem much, much faster than what you can do with maybe a GPU or some kind of electronic hardware. But today I'm primarily going to focus on this idea, the hybrid integrated photonics. And if you're interested in all those things, again, you can find all those information in my web page. There's also a lot of talks that I've given, recorded talks are there, and I'll be happy to chat if you have any questions about this. Okay. So why do we care about this kind of integrated photonics? And to understand that, let's take a brief tour to the history of computing. And I think we can say that computing probably has undergone with the most dramatic change in technology area in recent years. Right? If you think about the first transistor was invented only 70 years back, and it has already changed the way we kind of live our daily life. So this computer is called ENIAC. It's made of the first electronic computer made of vacuum tube. This is probably like 80, 90 years back. This was, of course, huge. With scaling, we got this kind of 1980s computer, which used to be like really small if you think about compared to that. But we know that, okay, things have gotten like much, 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 much smaller. Right? And all of us probably carrying many of these computers with us today. And that essentially what it means, this Moore's law, which essentially kind of tells you that how this whole increase in transistor happen, how all the miniaturization happen, for CMOS transistors has almost officially ended. It's not growing up that well. And this is actually an interesting time for the electrical engineers to kind of think about, okay, what's next? What is the next big thing in the hardware? There is, of course, a lot of interest in replacing CMOS. There are a lot of very interesting research going on in nano electronic devices. In my opinion, though, it's probably very hard to replace CMOS given the trillions and trillions of dollars has been invested in it. So I think computing is going to follow the same path what happened with paper, water, or electricity. These used to be very prized commodity, and in fact, they still are in some parts of the world, but in developing countries, we take it to be granted that we are going to get paper, water, and electricity. And I think that computing is going to be something like that we are going to get for kind of free or very easily. And this is already happening. We are living in the cloud city probably of the United States, right? And this data centers and cloud computing, what it does, that we don't store all our images in our computer or phone. We store it somewhere else. We don't buy very high performance server and computer anymore. We actually rent space from AWS or Azure to run these different kind of high performing programs. So what is this data centers and cloud computing? In a very, very simple term, it's a room full of lot of computers. And these computers are working with each other. And you are accessing those computers through some sort of, through online or through internet. But it's very clear to this future, and I will even argue that this is no longer future, this is already present, but as it's going to increase, we are going to have much more large, faster, high bandwidth, and energy efficient communication channels. Okay? Now it turns out that the metallic interconnect, which is what people generally use in electronics, is fundamentally high lossy at higher frequency. I mentioned that some of the essence of my research has been that there are some fundamental limitations coming from physics. Can we actually solve them? We talked about diffraction for the imaging system, but this is also a fundamental limit. It just comes from electromagnetics, that as we increase the frequency of operation, the metals become lossier and lossier. You cannot do engineering to solve that problem. Like physics is really telling us that we cannot do very high speed. So how can we solve it, right? And one of the idea is, can we use optical interconnect? So can we use communication via optics? And this is an artistic picture actually from Intel, and their argument is that if we have all those computers sitting in a rack, different of this rack are going to communicate with each other using optics. So how does it work? Like, what is an optical interconnect? So think about a computer, and that computer is giving some electronic signal. We are calling it it's high frequency, we are calling it radio frequency or RF signal. We take that RF signal and we modulate a device where an input is a light source, either a laser or light emitting diode, and we modulate that signal. And when you modulate that, then the signal or the data from electronics become transduced to optics. We do this signal conversion, and then this optical signal is carried via interconnect. Now, these interconnects are optical fiber, which are extremely optimized over many, many, many years. They are extremely low loss. And then this signal goes to another computer, and that computer has a demodulator, or generally a photodiode or photodetector, that gets back that electrical signal. Okay? So this is how an optical interconnect works. We have this actual interconnect, which is taking the optical signal, but we have two blocks. One block is the modulator block that takes the electrical signal, converts it to optics. And then we have a demodulator block that takes the optical signal and converts to electronics. And then, of course, the computers work on that, right? So how does this modulator works? So we probably know from freshman physics that if we have a material system, and the optical properties of this material system is given by what is known as index. We generally talked about just n. It turns out there is also an imaginary part that comes in the sum of the material. And if you have a length L, we know exactly how the electric field is going to change when the light propagates through this material system. And this depends on this n and k, or the refractive index of this medium. And by changing that n and k, we can change the phase and amplitude. And that's how the modulators generally work. Okay? Now, does optical interconnect actually exist? And the answer is, of course, yes. In fact, the internet signal that you are getting today probably has spent a significant amount of time being in the optical domain. Okay? So back in the days, AT&T put together a lot of optical fiber under the sea. So most of the time, your internet signal is actually carried in the optical domain. And somewhere, this optical signal gets converted to electronics, and you get it in your computer. Even in a metropolitan areas and in a wide area network, people are actually deploying optical fiber. So one of the examples some of you probably know is called Google Fiber. Even if in Seattle, Bellevue areas, in the rich neighborhood, you can actually get fiber to your home, and you can get very, very high-speed internet. So the optics are really kind of being used here, right? These are long-distance communication. In the other end of the communication, which is small distance communication, either die-level, PCB, or backplane, this is primarily electrical. And somewhere in between, we have this rack-to-rack communication, which is interesting for data centers and cloud computing. And optics is really trying to get into this rack-to-rack right now. There are several commercial products being sold, and the goal is to really go even here at the smaller and smaller length scale. So what is the challenge? So the main challenge is, as I mentioned, the optical interconnect itself is very, very low loss compared to metal. But we have these two stages of transduction, from going to optics to electronics and electronics to optics. Those has to be efficient to make sense for optical interconnect to come to even shorter distance. And that essentially means we need like more faster, low power modulator, sensitive detectors, and essentially we need new materials, new device, and increased light-matter interaction. Now, also, it is probably conceivable if you start thinking about that we have all those computers, and each computer has a modulator and detector. It probably has to be fairly small, right? So if you go to any optics lab, including my lab, you will see that this is actually messy. There are a lot of large optical components, and they are generally bulky. But this is what changed over maybe last 30 years. It is indeed possible to start thinking about that can we shrink optics from table to a wafer. So this is actually a fabricated wafer from Intel, and you can see each of these dies, and each of the die actually has optical, it's not the same function of optical table, but several optical devices sitting on the chip. So how do they look like? So photonic integrated circuits can really make this waveguide that can work as a communication channel. You can make something like mirror, beam splitter, and many of these devices we fabricate routinely in our lab and many other groups. Okay. Can you make switches? So there are two kind of main switching devices that people use for photonic integrated circuits to control light. One is a micro ring resonator. So in this case, it's called ring because this looks like a ring. So you launch light through this optical fiber, that or optical waveguide. It can couples to the ring and it can circulate, and that's how, by changing the N and K of this ring resonator, we can change the light transmission. So rings are generally used for resonant devices. And for non-resonant devices, we generally use what is known as a Mach-Zehnder interferometer. So we have two arms. In one of the arm, we change the N and K. So this arm, the light that goes to this arm, will have a different phase than this arm, and then we can interfere them. And by controlling the phase, we can change the amplitude of the light transmission. Okay? So these are the kind of some of the very well-used techniques that people have done in integrated photonics. Now, how do you change N and K? There are many, many different methods. And there are MEMS, there's a liquid crystal, then there's a thermal tuning that we are doing a lot of work there. Acousto-optics, Professor Molly's group and University of Washington doing a lot of work there. And then if you go to very, very high speeds, the free carrier dispersion is really kind of the workhorse for silicon photonics today. And then there's some very recent work on this lithium niobate, putting lithium niobate on chip, and we are getting this kind of modulation. Okay? And I showed you, like, essentially your speed kind of increases as you go from left to right, but the modulation amplitude also decreases. But all these things are volatile. What I mean by that this effect persists only when you apply a voltage. The moment you remove that electrical signal, the effect goes away. Okay? But anyway, even the fact that we can do switching and all those things has given rise to what is known as programmable silicon photonics. And going beyond optical interconnect, which really was the reason people started thinking about integrated photonics, nowadays you can really make large-scale silicon photonic circuits using foundry. People have looked into it for optical neural network, for quantum information. In fact, there are two startups, PsiQuantum and Xanadu. They have raised billions of dollars to using silicon photonics to create this kind of quantum information system. And so this is really conceivable at this point, that can we start thinking about a programmable photonic code. So you can think about, you have the same devices sitting, an array of those devices, they are identical, but then I go and program it and get new functionality. And this functionality could be different kind of filters, maybe different kind of resonators. So that's like really open, and that's kind of where it starts sounding similar to this field programmable gate array. But the problem has been that we have minimal tuning. So this tuning thing that I mentioned with the MEMS and liquid crystal and all those kind of other effects, the change in the index is very, very small, and that's why the change, ultimately the devices become very large, and they are volatile. That essentially means you have to keep on applying the voltage. So that's really kind of the two problem that I think reason the programmable silicon photonics are facing. Now, this kind of programmable photonics, can they help with optical interconnect that we talked about? And this is actually some of the work that we are doing with Intel. So I mentioned for the transmitter for optical interconnect, we have a light source and we have a modulator. Right? So if you connect the laser to modulator, if one of the devices break, the whole chip breaks. And then you have to remove that chip, introduce a new chip. And the idea is, can we actually make multiple lasers, multiple modulator, and put a routing network, a switching network here that we can program to connect only the functional laser to the functional modulator. If one of them don't work, we can just go and program it. Of course, again, you can think about it. You programming it means that we change it and then you leave it there. Like think about your flash drive, right? You put your data there. You're not applying any more voltage. We need that functionality which is absent. So in general, creating this redundancy, so having like multiple lasers, multiple modules connected together, and what is known as this kind of non-volatile trimming, so we make this device, can we actually control them, can we change them, are really important to scaling these systems. And so far, like a few years back, this functionality did not exist in integrated photonics. So we started looking into this material, a phase change material. It's a non-volatile phase change material. These are made of a material family called chalcogenides. And this material is by no means a new material. People actually have used that for electronic memory. In fact, many of the fab lines, including Intel and Samsung, are actually producing some of this material for electronic memory. And we are interested to see, can we use that for optics? So this material we grow by sputtering, and it grows in its amorphous state. Now, if we uniformly heat this material and make it to above a glass transition temperatures around 200 C, it goes to the crystalline state. And this too has very different refractive index. And then, if we put a short pulse but rapidly quench it, so with the short pulse we melt the material and then rapidly quench it, then the material goes back to the amorphous state. So using this kind of different pulse condition, different heating condition, we can go back and forth between the amorphous state and the crystalline state, and these two states have very different index. So let me spend a little bit time talking about pros and cons of phase change material, and I think it's very important as an engineer to really understand what are the problems with the material so we can identify what kind of application this is good for. So pros, as I mentioned, it's non-volatile. People actually have demonstrated that the material retaining its state for more than 10 years. It has a very high contrast, or essentially means the refractive index change that happens between these two states is almost greater than 1. And this is probably the largest change that you can have in any known material, the index change that we can get. We can also get multi-level operation. As I told you, that it goes to amorphous and crystalline, so it's kind of a binary operation, right? But by choosing the pulse condition, we can go partially crystalline, partially amorphous. So not just one transition, like 0 and 1, we can actually get multi-level operation. They can be changed somewhat fast, so picosecond to nanosecond for amorphization. For crystallization, we can also do like on the order of nanosecond time scale. So we can change them fairly fast. They are low energy. We don't need humongous amount of energy to cause this phase transition. And they are also scalable. What I mean by that, we can make them very, very small scale. They works fairly well. And potentially, they are CMOS compatible because many of these materials are actually already in the fab line of many of these electronic manufacturing facilities because they are being used for electronic memory. So what are the cons? So one of the cons is the phase transition condition can be very difficult to identify. So it takes a long time to figure out where the phase transition condition is. I'll like point out though, but once you identify, it stays that way. And it's important because some of the emerging material, like my group does a lot of work with 2D material. These materials are done by mechanical exfoliation or by Scotch tape. Some of you probably know it got a Nobel Prize in 2010. And that material is every time you make one, it's different than others. So it's not very repeatable, but these materials are repeatable, but we have to find the phase transition condition that could be tricky. So this material also has low cyclability, and this is the part that I actually really, really highlight all the time because often people in the community kind of forgets that. And it can do a billion cycle. Now, is billion a big number or small number? It really depends on what kind of applications you are doing. So for example, I talked about modulator, right? You are turning on and off a device. And generally, the speeds are gigahertz. If you run a phase change material in gigahertz speed, this device will die in a second. So many people who are trying to kind of improve this speed of this material probably doesn't really make that much sense. What it is good for, however, is kind of memory-like applications, what we were talking about, this non-volatile trimming. So if you have a 10 to the power 9 cycles in your flash drive, you can probably keep it for like 20 years, no problem, right? So it really depends on what kind of applications we are interested in. And that's why we chose these applications that really not for high speed, but for very low speed, infrequent, but it's non-volatile. So once you change it, nothing really, like, you don't have to keep on wasting energy. The multi-level operation is somewhat stochastic, and we'll show you some very recent results, very promising results showing almost 5-bit operation using phase change material. And then I think one of the maybe Achilles heel of this material had been the high optical loss. So you can see this material that I'm showing in N and K value, this material has a kind of large K, so imaginary part of the K. And imaginary part of the K essentially means light is going to get absorbed. And you don't really want absorption, because that means that your information is getting lost. So we have primarily figured out many different materials, and this is like one of the archetypal material for phase change material GST, which has this high loss, but we have introduced new material to tackle this problem. So when we started this, we started with kind of putting GST on the silicon microring resonator. And this is probably one of the first experiments people did on phase change material on silicon. Most of the previous work were done on silicon nitride. And this is how the device looks like. If you take a scanning electron micrograph, this is how the ring resonator looked like I showed you before. And this is where the PCM is sitting. And we can do AFM to figure out exactly where the PCM is, what is the thickness of this GST. So we did a very kind of thorough characterization of this material on silicon. And then we put together some setup. This is like an optical fiber probe to measure the transmission of this integrated photonics chip. And this is kind of how the result looks like. So I'm going to just make sure that everyone is on the same page. What happens in this kind of ring resonator, when you shine light here, some of the light gets confined inside this ring resonator. When the light is getting confined, it's not coming out. So you are going to, so when you measure the transmission, you are going to see some dips. And you will see multiple dips that comes from the fact that many different wavelengths can actually get confined in this ring resonator. But when we change this material from amorphous to crystalline state, you can see, so the blue one here is the amorphous state, and the red one is for crystalline state. And we did it for multiple different lengths. So my graduate student who did that GRU, he did a really kind of, he measured 400 devices to really understand what is the loss of this material, how reliable those material is. And kind of long story short, that we demonstrated reversible tuning of the GST on integrated photonics, and which we proved by broadening of the resonance and redshift from going from amorphous GST to crystalline GST. So redshift essentially means that your resonance shifts to a longer wavelength range. We also demonstrated quasi-continuous tuning and kind of an optical switch. So you can think about, if you put your laser here, you are getting a lower transmission. By changing this material, you can see a larger transmission. Right? And we did a demonstration up to 33 decibel. So with that kind of background, so our goal is to get to this programmable unit, right? That we can program. So what we need is electrically programming, because we want to create many, many devices that we can control electronically. We also need low loss. And also, these kind of ring resonators are somewhat resonant devices. They are not necessarily very good for broadband operations. If you think about some of this laser and modulator idea that we talked about, or this programmable silicon photonics, you really don't want to fix to only one laser. You want to have a larger bandwidth over which it can work. So these are the kind of remaining challenges. And in today's kind of talk, I'm going to primarily discuss 3 different class of experiments that we have done over the years to solve most of this problem. So we'll start with the electrical control. Okay? This is a fairly busy slide. I'm just going to tell you what to kind of think about this, right? So I told you the phase change memory is already present in electronics. So people are doing that. In their case, the material actually sits in the electrical circuit. And when you pass current, when you do the phase transition, its conductivity changes, and that essentially means that you see a change in different current. But the amount of material that you change is very, very small. The volume that you change is probably like 10 nanometer whole cube. So in optics, is a volume effect. What I mean by that, let's say I put a 10 nanometer cube particle here. No light is going to be blocked by that particle. So we need to have a larger volume of the material that needs to change to cause a change in the optical transmission. And many people, including us and some other community, we realized that we need to really come up with a new way of changing the phase change material that cannot be done in electronically, like electrical memory, and we used to use an external heater. So our heater will be, the PCM will be not part of the electrical circuit. We have an external heater. We'll heat it. Heat will diffuse through that material and cause the phase transition. That was the basic idea. And we spent a lot of time developing this model, multi-physics model using COMSOL. And we identified graphene is actually one of the best heater material. It's transparent. It has a very large thermal conductivity. but graphene is very difficult to work with. So we tried few things, and this is like almost 4 or 5 years back. And then my grad student had this really interesting idea that we are using silicon, and silicon, like what is the difference between silicon and let's say silicon nitride? Like an electrical engineer, you should know that, okay, you can dope silicon. You can dope silicon, which you cannot dope with silicon nitride or in dielectric. And that means we can create a PIN junction, we can pass current, and we can create heat. Now, this is a very, very simple idea, but for many reasons, people have not really thought about it before. And that was kind of his idea that, okay, instead of putting any other like graphene or other material which makes the fabrication more and more difficult, can we not just use the PIN junction here as the heater itself? So we just put only phase change material, and then we have a PIN heater. You pass current, and you can change that. You can actuate the phase transition. So these are some of the devices that we fabricated. Again, everything is done in the university using our university clean room. So we have a PIN junction. This is a zoomed-in view, and this is where the GST sits in. So it's actually fairly simple fab compared to graphene. I'm going to show you the graphene results in a bit as well. So first we did the characterization of the heater. So when you measure the current and voltage, you expect to see this diode-like behavior. It's a PIN junction, right? So all of you should know that. But when the material actually going from amorphous to crystalline state, it has a very large change in conductivity, but you don't see any change in the current voltage relationship because the material itself is not part of the circuit. It's an external heater, but you see a large change in the optical output. This is an output measured through the waveguide. So the light transmission changes, but the electrical resistance does not change. That essentially means it's an external heater, and we are changing a larger volume. So can we do these other properties, right? So reversibility, we actually tested that we can go back and forth between crystalline amorphous state on chip. And then this is showing the non-volatility. So we change the material, and we remove all the voltage, and it stays there. And then we do another pulse, change it back, and then it stays there. So this is done only for a few seconds, but we have done experiment for 4 months. The material holds their state up to 4 months. We have not done 10 years, of course. And then the endurance, that how many state reset cycles we can do. And this was, we showed the 1,000. And back in 2020, this was a record number of cycles that anyone showed that we can have 1,000 cycles. Now, 1,000 is a very small cycle. We are going towards this billion cycle. But before then, the number was 10 to 100 under electrical pumping. We also demonstrated that same thing with ring resonator. So we showed that this works for Majumdar interferometer, waveguide, and ring resonator. And we show the high endurance. But we knew that the graphene is this material that can give you very, very low energy. And one of my, another EC grad student, he kept on working on it. And it's an extremely complicated fab. There are multiple layers that's involved. But he ultimately was successful putting graphene on the phase change material. By passing current through the graphene with this very, very ultra-thin heater, he demonstrated that we can have, of course, phase transition and kind of record low energy efficiency. So this is kind of experiment showing that over many different wavelength range, we can get a broadband reconfiguration using graphene actuated GST, or this germanium antimony telluride material is one of the phase change material. We also demonstrated up to like 1600 switching cycle, showing that we can still preserve the endurance. But really kind of what is important here that we showed that with GST, there are 2 different phase change material we used, but the programming energy density that we can get is the lowest among all the ones that's reported. And very specifically, this is reaching what is limited by the thermodynamics. So we are heating up the material, and that is causing the phase transition. So ultimately, it is limited thermodynamically that what is the energy density you will need to change the material, which turns out to be around 1 attojoule per nanometer cube. And we showed the result to around 5 attojoule per nanometer cube. So we are also within an order of magnitude of the thermodynamic limit that we demonstrated with graphene. Okay, so let's now we talked about electrical control, that can we get really the broadband operation. So I told you like this works for like the broadband, but in this case, one of the state, you are still kind of getting all the light attenuated because the material is very lossy. We want our broadband operation, the light to not get lost, just light to get a different channel. Okay? I'll probably explain that what it means in a bit. So one way to do that is, as I mentioned very beginning of the talk, using a Mach-Zehnder interferometer. This is the device that everyone uses for broadband device. So what you want, let's say you put an input here. You want to get the input here or here. So that's what I was saying, that you don't want the light to get lost. You want the light either one port or another port, and you can do that by controlling one of the arm, by changing the phase. By controlling that phase, you can have either constructive interference here and destructive here, or constructive interference here, destructive interference here. That's how you can switch the light, but the light is never getting lost. So if you just naively think about using this kind of a Mach-Zehnder interferometer-based switch, you can find that due to the very large effective index, we can make a very, very small length using phase change material. However, what happens is this is where the loss comes in. This material also has a very high amount of loss, and the loss changes between two states. So when you change this material, in one port, light gets very, very strongly attenuated compared to the other port. So if you remember from your basic freshman physics, when you are doing interference, you have two light. One of them has almost zero power, one of them the high power. You cannot interfere them, right? I mean, basically the light remains same, so it doesn't really work. So again, we came up with an interesting device idea using directional coupler switch. So in this case, generally the traditional directional coupler have these two blue waveguide here, but we added a third waveguide in between, and we put the phase change material there. I'm going to tell you how it works. And some of these ideas we kind of came up independently, but it turns out people have thought about this even 10 years back. People have looked into some of these devices, even though they did not do experiment with that. So how does it work? So let's say you inject the light in one of the waveguide, and then the light is traveling through this waveguide. It can couple to the middle waveguide and come back to here. Okay? And by controlling this gap and or designing the gap and the coupling region, what we can do using one of the state of the material, for example, amorphous state, light comes here, couples to the middle waveguide, comes out here. So we can get light from one port to the another port. But then when you do the phase transition and we make the material to crystalline GST, you are actually changing N and K both, and that changes the interference condition significantly, so light just comes straight and come out here. So what happens here, that in one state, the light actually not sitting in the middle waveguide at all, where the phase change material is sitting. And in that state, the phase change material, or GST in this case, actually higher loss. So even the material itself is lossy, by device engineering, we can make sure that the total loss of the device remains very, very small. So we did fabricate this device. So you can see that this is an optical microscope image. If you zoom into it, we have a 3 waveguide, and this is a false color showing that where the PCM is going to sit. And we demonstrated almost less than 1 dB insertion loss, even when the material loss is very high. So if you just put the material on the waveguide, you are going to get a loss of almost 10 dB. So we have reduced the loss by factor of 10 without really touching the material, just by designing some sort of devices. Okay, but can we do electrical control? This is just showing that by optically that we can change. So this was a little bit challenging. The reason is that when we introduce this third waveguide, the price we pay, our device length become much larger. So the phase change material that we need to change, that volume of that get much larger. So we had to re-optimize our heater geometry. We still again use the PIN heater, but with that we demonstrated a broadband operation and reversible tuning. So we are essentially measuring this bar port and cross port. So one time the light comes out in the bar, then the light goes to the cross. Sorry, in this case it comes out in the bar port, then the cross port, and then it go back to the bar port. So we can change the phase transition, and we can reversibly tune and reversibly make sure light comes out in the top waveguide or the bottom waveguide. And we demonstrated up to 5,000 cycle here. So this is again, at that time it was a kind of record high numbers. Our loss, however, was somewhat larger, and this is kind of the reason is this fabrication is fairly complicated. All the fabrication is done in the university, and I mentioned very briefly that we are actually working with Intel trying to put PCM on Intel silicon photonics, and we believe that that will reduce the loss, because theoretically the loss could be as small as 0.1 dB. Okay, So the last part I'm going to talk about that can we now start thinking about new type of phase change material that really even give you much, much lower loss. So this GST, the material that we are working with, actually has very high loss in one of the state. So we are working with two different materials. We did not really invent this material. These materials were there in the literature. We essentially learned about this and we started working with this. So one of the material is called antimony sulfide and the other material is called antimony selenide. And you can look at there, this material loss value is very close to 0 in both the state, the amorphous and crystalline state. Okay? So these are two materials that we are working with. I'm going to primarily show you some of the results on the SBS. So what is the kind of price we pay for this high loss? One of the problem is that the delta N, the change in index actually goes down compared to GST. But secondly, as I mentioned before, that finding the phase transition condition for the new materials becomes very, very difficult. So this material, primarily this SBS is what we are looking into. Before we started our work, no one has demonstrated electrical demonstration, and optically also the phase transition was not done like for many, many cycles. So we essentially demonstrated electrical control of the SBS. And I'd like to point out here that what is the thing that we did differently than what other people did not. So when the phase transition happens, in one of the state, you are actually melting the material. So the material is essentially liquid on the chip. And if you don't contain the material, this material can flow off. In fact, when the device breaks, sometimes we see a bubble. If you put it in the scanning electron micrograph, you see a bubble in the phase change material. That means the material has left and some of the air has flown in. So we encapsulated this material very well, and that requires some fab tricks to make sure this material is covered with alumina in all the dimensions. So essentially, even though when you are controlling this material, changing this material, it doesn't flow off. Okay? There are a few more tricks to it. One of the things that we found for this particular material, that when you are doing the phase transition, I told you about change in conductivity, I'll tell you change in N, but it also changes its volume. So that you have to really make sure that you give it enough space so the material to actually thermally expand or thermally contract. So there are a few tricks and few fab techniques we had to develop for that, but ultimately we were successful to demonstrate that in this device, here's a ring resonator. So the blue one is in amorphous state, and by applying the field, when you change the material from amorphous to crystalline, we can go back. We can change the cavity resonance, and then we can go back and forth. This is almost like 10 cycles that we demonstrated here in the ring resonator. Then we demonstrated a Mach-Zehnder interferometer. Just if you remember correct, for GST, we could not do the MZI because of the loss of the material. But here we can actually, because the material is low loss, we can just use simple Mach-Zehnder interferometer, and we demonstrated broadband operation using this Mach-Zehnder interferometer and SBS platform. Some more other devices we demonstrated. All of them are essentially showing that we have low loss, and we can actuate then in multiple different devices, and we can get more than 10 dB extinction ratio and fairly low insertion loss, which was not possible using phase change material. We also demonstrated up to like 1600 cycles. So as I mentioned that we observed 1600 switching events thanks to like this kind of improved fab. The previous reports were only 10, was the 10 number of cycles that people have reported. But probably the most interesting part that we saw is this multi-level operation. So I told you the phase change material can go between amorphous and crystalline state, but judiciously choosing the pulses, we can drive the material to partially crystalline and partially amorphous state. And this was done before with optics, but we demonstrated in the electronics in this material that you can see here this experiment is done over 10 cycles, and we can clearly see around 32 levels, so 5-bit operation in this material. So by changing the electrical control judiciously, we can get to this, go to these intermediate stages. So what it is good for, right? So one of the thing that we demonstrated, so when you make this kind of Mach-Zehnder interferometer and the balanced Mach-Zehnder interferometer, you can do your math, and you will see the light actually should always come out in the cross state. But due to fabrication imperfection, and this is what I was showing before, that you fabricate this structure, and once you fabricate, you cannot really do anything. It just is this way. That was the state of the art. So we essentially get an MZI with lower extinction ratio due to fabrication imperfection, but then we can control that SBS and slowly drive the SBS to make sure that we increase the contrast. And this is a non-volatile. We essentially fabricate something, then we change it, and it kept this way, and we just essentially get a new circuit. So this is kind of showing that how we actually did that. So here we are slowly driving the material. We come back here, then we go past here and come back here. And I would like to point out here is this is how everyone who work in optics actually did align their setup. We essentially, by hand, we make sure that we maximize the signal or minimize the signal. We go past that point, and then we come back. And in some way, you can think about we are essentially doing a gradient descent in our brain, right? That we are figuring out that where is the minimum, and then we come back. And that was not possible before with a binary switching. But with this multi-level switching in both directions, we can actually go past and come back. And this is the 3 devices that we have demonstrated. So 3 times we have demonstrated showing that this is indeed repeatable. So with that, I'm kind of coming to the close of the talk. So what I demonstrated here that we found this new material, phase change material, that brings some unique functionality, that this non-volatile tuning, non-volatile programming that was not possible in integrated photonics. And we demonstrated with the silicon PI heater and graphene heater with up to 5,000 cycles. Of course, we need to do much more. And with the graphene heater, we demonstrated really the fundamental limit of energy efficiency. We demonstrated broadband programming, a programmable unit. Even though there is a large amount of material loss, we can definitely mitigate that with the device engineering. And finally, we also talked about these 2 different PCMs, the SBS and SBSE, which really can give us very low loss operation and also multi-level switching. Okay? So really, what happened? What changed in the 5 years? Right? So we believe that a set and forget type of functionality was missing in photonic integrated circuit. And what I mean by that, like if you go to any optics lab and you are buying an optics, all those optics comes with 2 handles generally, right? And you are essentially, what do? You can work the beam or change the beam shape. You do a lot of things with them manually and all those things. But once you align your setup, you lock the setup. This was not possible in the sense like when you fabricate something, it is kind of locked. You cannot control it that way. And this is exactly, I think, what we achieved in PIC, that this kind of set and forget type of utility, it was not there in PIC before this phase change material. And this really opened up a lot of opportunities. So we talked about some of the work in doing in PIC. There's a recent perspective paper we wrote in the opportunities and challenges on the phase change material, but we are also looking into this kind of free space optics. Can we use PCM in some way? And I'll outline that what is kind of really the big challenges, that can we get an endurance to 1 billion cycle? Can you reduce the loss to 0.01 dB? So this is at least an order of magnitude lower than what we currently have demonstrated. Sub-1-volt reconfigurations. This is where the CMOS thing comes in, that you can, of course, do higher voltage in the lab, but ultimately the goal is to put them with the CMOS. You don't have that much voltage from CMOS. So can we do that? And of course, another direction is, can you go to the visible wavelength range? So all this work that I showed you is in 1550, 1310. But once you go to visible, it actually opens up some interesting opportunity to work with quantum emitters. So the quantum emitters generally emit in the visible wavelength. So can we do this kind of non-volatile reconfiguration in the visible wavelength range? So these are the 4 things that I think is really the community is interested in and we are working on. But what we have right now, right, with that, we think we can start looking into foundry integration and start creating some of this kind of non-volatile switches for neuromorphic optical computing. So this will be more efficient than what current state of the art with the thermo-optic tuning. So I'm going to stop here, and I'll be happy to take any question.
We have time for a few questions from the audience.
I have a question about the switching and the cycle number. you say you did it for, like, in this graph 1,000 times. I don't see any degradation, though. You just stop at 1,000 because it takes a long time? Or, and also,
correct.
what is the reason that there's a limit?
So I mean, you are right. The 5,000 cycle, it did not degrade. So, and we had to kind of stop it because this experiment, if you see, like, we generally do take like 1 second per cycle. So it takes a significant amount of time to do it. But at some point in time, it is going to degrade. So, and the reason the degradation is some oxidation of the material. And the other time you can think about that the material is basically changing back and forth. So every time it's changing, not all the atoms come back in their own position. So one of the thing that people are very interested, if we can get a monoatomic phase change material, that will have infinite number of cycles. But that doesn't exist. And I know that Professor Anand here has looked into this kind of stuff before, but yeah.
Okay. Do we have another question? Yeah. Yes, you're too far away.
So, intuitively, the PIN heater seems like a pretty logical way of doing it. And so I just didn't really understand why, from an intuitive level, what advantage does graphene have over the silicon or the doped silicon? What is different about it?
Yeah, so I think the question is that why we want to do graphene with integrated silicon PIN heater. So the reason is we wanted to get lower voltage. So basically, if we go to sub 1 volt, and there is no way the silicon can get you sub 1 volt. The reason is you are essentially heating a larger area of the heater, and with the graphene you can heat a very, very thin area. So that's what you give the more energy efficiency. But having said that, from a practical perspective, I think most of the scaling we'll be doing is with silicon till like someone figured out how to scale graphene. No one has figured that out. But also graphene is cool. So.
Do we have one more question? Yeah.
So with the graphene, you can cover just the PCM, whereas with the PIN heater, you have to cover a larger area?
Not just that. The other thing is that if you think about like the area that you are heating it up with the PIN, that's basically the whole silicon volume. So 200, like you can think about 220 nanometer thickness of silicon. Graphene is like 1 angstrom. So that's where the energy efficiency comes in. Yeah.
Okay. I do have a question. So since you work with Intel, right? So the phase changing material is so promising. If Intel is willing to invest millions of dollars to develop them, it seems they can make anything happen, right? Like a FinFET, when it's just proposed, sounds incredibly difficult to make. So what will be the tipping point that you actually can convince Intel so fully goes into investing in PCM for the photonics service? What are the big breakthrough or challenge you think you can overcome?
I mean, like I worked in Intel for some time, and Intel's philosophy is that they need to see like certain things working before they will start investing. So right now they give us like 100K, 200K. It's not that much money. So I think if we demonstrate this, if we demonstrate a 1 billion cycle and the 0.01 dB loss, because they really don't want any loss, light getting lost. So if we demonstrate this too, and I think, so they are looking into that. And so if we can get those, then they will be like super excited to put the material. And I'll point out here, the material that they can work with is SBS and GST. Any selenium is not allowed in Intel's fab. So selenium will not be used. It's a toxic, it has some toxicity.
How do we possibly demonstrate a billion cycle if it will take a billion seconds to demonstrate?
No, so I think this one we have to just switch it faster. So the way our experiment is done, we always check for non-volatility, but we can do like billion cycle, like we can test it. But we don't know that the billion cycle will work. So we have few ideas. One of the idea actually was inspired by some of your work, that instead of a continuous film, like can we make like small islands, and that expect to give higher endurance. So good thing is with Intel now we have like 200 chips. So we don't have to start with every chip they fabricate from the scratch. So we are going to try some of these PCM ideas to see how it works.
Great, wonderful. With that, let's stop and thank Arka again. Thank you for coming.